Hello everyone, welcome back to the workshop. And our next speaker is Professor Michał Pilipczuk from University of Warsaw, and he'll be talking on randomized methods and parameterized algorithms. Thank you so much for joining us, Professor. Over to you now.
Yeah, thanks a lot. So I will be talking about randomized methods in parameterized algorithms, more precisely about color coding technique today. Just for the logistics of this talk, I hope that you hear me well and you see on the screen the sort of presentation. So we'll be going through those notes and fill them during the lecture. So this will be not a standard slideshow, but rather a more interactive thing. Also, please feel free to interrupt me at any moment with any question. Note that you will be heard and recorded if you ask a question. And also at some point, just to make sure that we are on the same page, I will ask you to write in the chat a +1 if you understand what is going on at this point, so that I am also comfortable with the fact that that you are following the arguments that are done at this point. Good. So we are going to talk about randomized techniques in parameterized algorithm, and more precisely, during this hour, I will present to you a technique called color coding, which is the most basic technique of randomized, how randomization comes into play in parameterized complexity. There are actually two major sources of randomization in parameterized algorithm. One is color coding, and another one is algebraic techniques that we will not cover during this lecture, mostly because of just the lack of time. Both color coding and algebraic techniques, they deserve at least one lecture each to present in details. And I thought that the color coding is just the more basic one, and therefore we'll focus on that. So color coding, in the way that we will describe now, was defined was introduced by Alon Neuster and Zwick in I think 95 in their paper about the K-path problem. K-path will be actually our first example in a moment. So this is a very old technique. It's essentially as old as parameterized complexity itself. However, it is useful as a basic tool. Part of the toolbox in many different algorithms in parameterized complexity. So to explain the technique, let us fix the problem that we'll be solving. And this will be the first example that was used by Alon Neuster and Zwick, namely the K-path problem. So we are given as input a graph G that is directed. Well, it will not play a very large role that it is directed, but let's fix it to be directed for a moment. And I've got some integer k. This is the length of a k-path that I am looking for. And the question I am asking is whether in G I can find a simple path on k vertices. And by simple path, I mean simply a path that has no repetitions. So for instance, if you look at this graph on the right-hand side, I could, for instance, start in this vertex and then go by a path to here, then to here, then to here, then to here, then to here, and then to here. Yes, and see that this is a path on 7 vertices, if I'm not mistaken, and it follows the orientation of the arcs, right? So this would be a 7 path. Right, so the question is simply whether I can find such a path on k vertices in a given directed graph. So note that if I ask for k equal to n, then this is equivalent to the Hamiltonian path problem, right? So the problem is NP-hard. NP-hard in general, because it for a particular value of k, it generalizes an NP-hard problem. However, we will think about k being small, as in parameterized complexity we usually do, and we'll try to make an FPT algorithm for this problem parameterized by k, the target length of the path. So it is useful to think when approaching this problem of the following variant. That will be the most important variant for us, namely a colorful variant where the vertex set is partitioned into several layers or colors. So layer 1 is color 1, color 2, color 3, color 4, up to color k. And we are looking for a k path that is properly colored. So this condition will be called a properly colored. And the condition says that I won't like to find a k path such that the first vertex is colored with color 1, the second vertex is colored with color 2, the third vertex is colored with color 3, and so on, up till the last vertex is colored with color k. Yeah, so I am given a prescribed partition of the vertex set into k colors, and I am really looking for a k path that really is compliant with those colors. Yeah, first the if vertex is of color I. And if you look at this variant of the problem, it is actually much simpler than the original variant of the problem. For the following reason, that we can solve it actually in polynomial time using a very simple dynamic programming algorithm. Namely, at every point, we will look through consecutive layers, and when looking at layer I, we will store for each vertex of this layer I whether there is a path that looks like this on the picture, that it looks like that starts in the first layer, then goes to the second, the third, and then ends in layer consisting of vertices of color I. So how do you do this using dynamic programming? Well, this is very simple. So for every vertex, let me define this function phi of w for every vertex w. From layer I, this will be just the Boolean value. Is there a path looking like that? So is there a properly colored path v1, v2, v3 up to vi, which is equal to w, such that each vj is of color j, right? So if I define this function or this Boolean value, right? Sorry, then I can easily write a recursive formula for computing. So if I'm looking at layer 1, so all the vertices of color 1, yes, then clearly I have always a path ending this, because this is a path consisting of just one vertex. So this is the base case of the recursion. And then the recursive formula, if I would like to understand whether I can find a path looking like that ending at vertex w, I need to iterate through all the possible in neighbors of w and check whether there was one shorter path that ended in any of those vertices. Yes, so I make a big disjunction over all the vertices u, yes, that are predecessors of w from the previous layer, and I check whether there was a path looking like that ended in one of those predecessors, because then this path can be extended to a vertex w, right? So if I now would like to understand whether there is a properly colored k-path in the whole graph, then I simply check whether any of the vertices in the last color can be accessed by a path looking like that. Right, so this variant of the problem is indeed in p-time, can be solved in polynomial time. So now we would like to use this variant, this algorithm that we have just seen, to make an FPT algorithm for the general variant of the problem, where no colors are given at the beginning on the graph. So just to make sure that we are happy with this argument, if you understood this argument, please put a +1 on the chat, and if you did not, please ask a question so that we clarify any doubts at this point. Don't be shy, put +1 if you got it. Okay, I see a number of +1s. This will be our procedure for making sure that the stuff is understood. Good, so now we would like to reduce somehow the general case to the case where the vertex set of the graph is colored. And the trick is to choose this coloring at random. So for every vertex w from the graph, I will pick a color of this vertex I from the set from 1 up to k uniformly and independently at random. So for every vertex, I just throw a dice with k size, and depending on what the dice told me, I put a particular color on this vertex, right? So in this way, I randomly choose a partition of the vertex set into k colors. So suppose that there is indeed a k path looking like that in my graph, yeah, v1 up to vk. What is the probability that that under this random coloring, this k path indeed is colored as we want, with color 1, 2, 3, 4, 5, 6, k, right? Well, the first vertex is colored properly with probability 1 over k. The second vertex is independently of this also propered with color number 2, yes, with probability 1 over k, because there's one choice of color out of k many, right? And so on and so on. The path has length k, right? So the probability is 1 over k to the k, right? So if there exists a k path in my graph, then with probability 1 over k to the power k, this k path is properly colored, right? So now here is our algorithm. I will pick a coloring at random, just as I said. Every vertex is colored uniformly and independently at random with one of the k colors. And then I check using my p-time algorithm in time that is polynomial, whether there exists a properly colored path. So clearly, this algorithm is randomized. Well, I chose some vertices at some colors at random. The complexity is polynomial because everything I do, I run my polynomial time dynamic programming algorithm. If there is no k-path in my graph, then for sure the answer will be no, because there's if an algorithm finds a k-path, a properly colored k-path, it is in fact a k-path in the original graph. However, the crucial point is that if there exists a k-path in the original graph, then this k-path will be colored properly with probability 1 over k to the power k, and my algorithm will be able to find it and answer yes, there is a k-path in my graph with probability at least 1 over k to the power k, right? So we have a polynomial time algorithm for the k-path problem, which almost always answers no. But if the answer should be actually yes, with some tiny probability, it will be actually able to find this answer yes. And the crucial point is that this probability is roughly like 1 over function of k only, and does not depend on the size of the graph. So now we can take this algorithm and just boost the error probability. And boosting the error probability in randomized algorithm is done often via a very simple trick, namely repeating the algorithm many times. So what I'm doing, I'm just repeating the algorithm k to the k times. Yes, and if the algorithm at any point said yes, then for sure it found the k-path in my graph. And if at all times my algorithm said no for the k to the power k iterations, repetitions, then I'm answering no. So let's see what is, so of course, if the algorithm answers yes, then it is sure that the answer should be yes, it just found the k, right? However, if it answers no, what is the probability that it made an error? So what is the probability that the answer was actually a no, there is no k-path, if there existed a k-path in my graph? Well, it needed, the algorithm needed to make the wrong assumption, to make a wrong coloring in each of the repetitions, right? So in every repetition, it makes a probability with, it makes an error with probability 1 minus 1 over k power k. Yeah, because the probability of finding a k-path is 1 over k to the power k. And then I repeat this experiment k to the k times, right? And therefore, I need to have an error in each of those repetitions, and this is why I'm multiplying those probabilities, right? So now I use the classic inequality from calculus that 1 minus x is smaller or equal than e power minus x, right? Which means that this is smaller or equal than e power 1 minus k to the power k times k to the power k. Yes, this cancels out. This is e2 minus 1, which is smaller than 1/2. Right? Which means that now that I repeat the algorithm many times, I actually managed to decrease my error probability yes, from 1 minus 1 over k to the power k, which is very, very close to 1, to actually something that is smaller than 1/2, right? So now the algorithm, if I repeat it, runs in FPT time, yeah, k power k times polynomial in n, yeah, because I have this many repetitions, and each of the repetitions applies a polynomial time dp in polynomial time. And let's observe what is the what about the error probabilities. If the answer to the problem should be no, then for sure the algorithm cannot find the k-path, so it will answer no, right? But if the answer is yes, then the algorithm will return a yes. It will find the k-path with probability larger than 1/2. So this probability, this algorithm is an algorithm with one-sided error, because the algorithm can err only on one side in having a false negative, which means that it says no when the answer should be yes, and this false negative is with probability smaller than 1/2. Right? And this is a typical scenario of randomized algorithm in parameterized complexity, that we are trying to find some object, and there is a randomized procedure that with good probability finds this object, so we get a possibility of false negative if we are unlucky and did not find the object because we chose a bad coloring at random. Good. So this is a basic FPT algorithm for k-path using color coding, and essentially this application covers the main points of the technique. So now we will improve. So before we will in a moment improve the running time to something like from k to k to 2e power k, where e is the base of the natural logarithm. However, before we continue, are there any questions at this point? And otherwise, if you do not have any questions, please put a +1 in the chat. Oh, there is a long question. Is there some way of quantifying the difference in the performance between graphs that have a lot of k-paths versus those that do not? This is, I think, a good question. I think that there were, in the algebraic framework, there were quite some works on trying to get better algorithm if the number of k-paths in the graph is large. I don't know of any precise works on this using color coding. It's quite hard, I think, to analyze this. However, you should look through the literature on algebraic techniques. I think that Holgerdal and others were doing stuff around this. Good. Yeah. Any more +1s if you are happy with this algorithm? Good. I see a wave of +1s. So we proceed to improving the running time to single exponential, to 2e power k times a polynomial in. And the trick is that instead of looking for properly colored k-paths, k-paths that really color the vertices 1, 2, 3 up to k, we will be looking for k-paths that are only colorful. And this means simply that vertices of the k-path are of pairwise different colors. So now I only insist that they are of pairwise different colors. So maybe I start with color 4, then I go to color 2, then I go to color 3, then I go to color somewhere else, maybe then color 1, and then maybe color k-1, and maybe I will actually end with color k, right? So now I just want to use pairwise different colors for the vertices of the k-path instead of having them exactly as in the order prescribed. So now let's prove the following lemma, that we are still able to look for such k-paths pretty efficiently in the parameterized sense. So I claim that we can verify whether in my graph there is a colorful k-path in time that is not polynomial anymore, but good FPT algorithm. So 2 power k times polynomial in. And the proof is essentially a very basic application of dynamic programming on subsets of colors. So now instead of saying, is there a k-path, a properly colored k-path that ends at a vertex W, I ask, is there a colorful k-path that ends in the vertex W and uses only colors from X and uses all the colors from X. So say that here are the colors X, say that these are the colors, and I ask whether there is a k-path that is colorful and looks like that. It uses all those colors and ends in W. Right? So now we can similarly give a dynamic programming formulation for this problem. Simply, if I would like to understand whether there is a k-path looking like that, yes, then this k-path needs to look like the k-path, sorry, not a k-path, it's actually a colorful path. It needs to look as a path that is trimmed by one vertex. So it needs to end in some in-neighbor U of W, and it should cover all the colors of X apart from the color of W, right? So in order to understand whether this value should be true, whether there is a colorful k-path using colors from X that ends in W, I need to iterate through all the in-neighbors, feasible in-neighbors of W, of colors from X minus the color of W, and I check whether there is a path that uses all the colors apart from the color of W that can be then extended by one vertex. Right? So now, in order to check whether there is a path that uses all colors, I need to just make a big disjunction over all possible endpoints of such paths of the values that I compute. Right, so how many values phi of xw we have to compute? Well, for w we have n options, where n is the number of vertices, and for x this is a subset of colors, all possible subsets of colors. So there are 2 to the k options because there are k colors. So we have 2 to the k times n values to compute. A computation of each such value takes polynomial time. So the complexity of this dynamic programming procedure is 2 power k times polynomial in n. It's essentially the same dynamic programming that you have seen probably for Hamiltonian cycle or TSP. Good. So now we have a procedure to find whether there is a colorful k-path in the graph. However, it is definitely has a worse running time than the procedure for finding a properly colored k-path. Now it runs in FPT time instead of polynomial, so we should gain on something. And not surprisingly, we will gain on the probability that the k-path becomes colorful, right? Because now for if there is a k-path in my graph, if I draw a coloring at random, it is more probable that it becomes colorful than before, right? Because now I have less restrictions on the coloring of this k-path that I expect. So what is the probability that this k-path becomes colorful? Well, so now how many colorings there of the k-path there are in total? Well, k power k of them, right? Of those k vertices, because each of them can be colored with k different colors. And in how many colorings the path becomes colorful? Well, k factorial. Well, because I need to choose a permutation of colors over the vertex of the k path, right? So the probability that the path becomes colorful is like k factorial over k to the k. So if you now apply Stirling's approximation of the factorial, you get that this is bounded by 1 over e to the k. So now instead of 1 over k power k probability, we've got a much better probability of finding a k. Sorry, this should be actually the other way around. Yeah. I hope that this inequality is actually in this direction. It is definitely in this direction up to a polynomial factor. Good. So we have now a much better probability that the k-path actually is colorful under. Yeah. So we need to repeat our algorithm, not k to the power k times, but only e to the power k times, right? So 2.73 to the power k. Yeah, to get an error probability is more than 1/2, using the same calculation that we had. So now what is the complexity of our algorithm? We have this many repetitions. Yeah, e power k repetitions of our algorithm. And each time I'm applying my algorithm, I use this this running time 2 power k times polynomial in n to solve the problem of finding a colorful k. So all in all, the algorithm runs in 2e power k times polynomial, which is FPT, right? So I now improve the running time like that, using dynamic programming on subsets of colors as a base subroutine. Good. So so already on these two examples, we see some features of this technique, and I think that it is good to pause now for a moment and think what actually happened. When solving k-path, essentially what is important are the disjointness constraints. So the important constraint is that the k-path cannot repeat vertices. So essentially the different parts of the k-path need to be disjoint from each other. And somehow color coding is used to reduce disjointness, yes, so non-equality of two different things, to searching for those things in separate universes. So what we did by coloring the universe, the vertex of the graph at random, we separated the search space for the first vertex from the search space for the second vertex, and so on, so that the disjointness, the non-equality constraints become trivial, because if things are taken from separate universes, there are for sure different, right? However, for the estimation of probability, we needed to look for small objects, right? The fact that the k-path only consists of k vertices was crucial when estimating that the probability of an error is only 1 over a function of k. All right, and these are the two basic meta observations about when color coding can be applied. So in a moment, we will see 1 or 2 more examples of application of color coding, just to give you a feel of how to use it and in what different situations it can be used. But if you have any questions at this point, please ask. And otherwise, you can put a +1 if you're happy with the algorithm. Okay, good. I see some +1s. We can go further. So now my second example after the k-path problem will be called a sparse set. I'm not sure if this is a canonical name, but let's live with it. So the input is an undirected graph and 2 integers, k and l. And I ask whether I can find k vertices in my graph. Maybe here some vertices, maybe here some vertices, so that the total number of edges that are incident on any of those vertices, yeah, so total number of edges that have at least one endpoint among the blue vertices is at most L. Yeah, so there are I need to pick k vertices so that the total number of vertices incident to them is at most L. So I will now show you a 2 power k plus L times polynomial time algorithm for this problem using color coding. And it is based on a very basic observation. Yes?
Yeah, there's a question in the chat. How do we know if we can't do better in terms of complexity?
The question about the k, is this question about the k-path problem? Yes. So about this running time, 2e power k times polynomial in n. So actually we can do better. K-path can be solved in directed graph in time 2 power k times polynomial in n using algebraic techniques. using multilinear monomial detection, and in undirected graph even in I think 1.66 to the power k. Under the exponential time hypothesis, you cannot do sub-exponential in k time algorithm, so 2 power small o of k. I guess at some point exponential time hypothesis will be covered later on. Yeah. So yeah, this is not the best algorithm for k-path that we know, but it is one of the simplest ones. Good. So going back to the sparse set, our goal is to get 2 power k plus l times polynomial time algorithm. And the basic observation, a very trivial one, in fact, is that if I've got at most L edges sticking out of my set X, that is a solution, and I look at the set Y, which is the all the neighbors of vertices of X. So Y is the neighborhood of X. Then clearly, if there are only at most L edges going outside of X, then Y must be of size at most L, right? So we have now 2 sets, one of size at most L, and second set X, which is of size K. And we will try to apply color coding in order to distinguish those 2 sets, in a sense, to look for those 2 sets in different parts of the universe. So how we will do it, we will color every vertex red or blue independently at random. So for every vertex, I flip a coin. With probability 1 half, I color it red, and for probability 1 half, I color it blue. So suppose I've got some solution X. Yeah, I fix some solution, supposing there exists one. So now let me consider the following good event. This is the experiment that I'm now conducting. The random experiment, and in this experiment I consider myself lucky. I have the good event if the whole solution X is colored red, yes, and the whole Y, the neighborhood of the solution, is colored blue, right? So what is the probability that the good event happens? Well, every vertex of X, there are k of them, must be colored with probability 1 half properly. So this is 2 power minus k. And every vertex of Y, the one that the neighborhood of X, should be colored with probability 1 half blue. And there are L of them. So the probability for this is at least 2 power minus L, right? So the probability that the good event happens is 2 power minus k plus L. Yeah, this already rings a bell when it comes to the complexity we are looking for. Yeah. So supposing that this good event happens, that means that X becomes fully red and Y becomes fully blue. How quickly can we find the solution? So first observation is that if we have the solution X, yes, then if we are happy, if we have the good event happening, yes, then the blue vertices, they need to be entirely disjoint from X, right? Because X should be colored entirely red. Yes, so no blue vertex can be in X. Yeah, so for sure we know that blue are not containing anybody from X. And if I now look at the connected components of the red vertices, so I look at the graph induced by the red vertices and I look at their connected components, then every such connected component should either entirely go to X or entirely go not to X. Yeah. Why so? Well, if X consisted only of, say, half of this component here, yeah, then there would be a vertex, yes, that is neighboring this part within this red component, which is a vertex from the neighborhood of the solution that was colored red, and all the vertices of the neighborhood should have been colored blue according to our good event. So this means that indeed every connected component of the red should entirely go to the X or entirely go not to the X. Right. So this means that now our problem of finding X, of finding a set of vertices such that there are only at most L edges going out of the vertex of X, essentially boils down to selecting some of the red components. Yeah, because none of the blue vertices can go into the solution, and each of the red components can either go entirely or not go at all. So each of the components, say this component here, C, well, it has some number of vertices inside, say AC, and there is some number of edges sticking out of it. Yeah, maybe edges like that as well. Yeah, so there are AC vertices and say BC incident edges. I see that there is a question. It's also more expensive if you wanted to randomize as well, right? Yeah, the randomization will go to the randomization at the end. Yes. So going back to this, every component, every red component, it can be characterized by two numbers: how many vertices it brings to X, if it is included, and how many incident edges it brings to the incident edges to X. Yeah. And now the question is whether we can pick components with a total number of K vertices in total, so that we include in those incident edges at most L of them. And now you can easily see that this is nothing else than an abstract problem. We have items. Each item can be taken or not. Each item is characterized by two numbers: how many vertices it brings to our knapsack, and how much we need to pay for this item. Yeah. And now the only thing that we need to understand is whether we can pack the knapsack full with K vertices, yeah, while achieving the smallest possible number of incident edges. So I hope that you all on your basic algorithmic courses have seen a p-time algorithm, a strongly polynomial time algorithm weakly polynomial time algorithm for the knapsack. So this problem, this question can be solved in polynomial time, right? So to summarize what just happened, the probability of good event is at least 2 minus is 1 over 2 to the power k plus L, yes? And supposing the good event happens, we can find a solution in polynomial time, right? So now what we need to do, again, is that we repeat the algorithm 2 power k plus L times, which means that we will have a randomized algorithm with false negative with probability at most half. And for each repetition, we try our polynomial time subroutine to find the solution. So the overall complexity is 2 power k plus L times polynomial in N. And again, if there was no solution, then the algorithm cannot find the solution. If there is a solution, the probability of finding one is at least half. Good. So are there any questions at this point, other than the randomization? Maybe some plus ones to make me feel better. Yeah, good. I see that that we are still following. So let me just make a small remark here that in this algorithm, our running time was something like 2 power k plus L. And this came from the fact that that we are taking this random coin flips with probability 1/2, and the probability of being red and probability of being blue was the same. However, if we are expecting to have many more vertices in the neighborhood than in the set itself, so k is say much smaller than L, then it would make sense to bias the coin, right? To make the probability of taking the red vertices smaller than the probability of taking the blue vertices, because then the intuition is that the probability of having the solution properly colored would be better. And indeed, if you do the maths, if you put the probability of being red k over k plus L and the probability of being blue L over k plus L, then the probability of a good event is k plus L to the power k times L plus over k plus L to the power L, yes, which after some calculations boils down for, actually this should be k plus L, for k smaller than L to k plus L to the power order of k. Yeah, so you can also express this probability in this way if you bias the coin. So observe that, for instance, if say L is equal to 2 power order of k, then this boils down to to 2 power order of k squared. While in the original setting, we would have 2 power k, right? So by biasing the coin, if L and k are really not equal, you can actually play with the probability and get better probability of L. Good, but this was a side remark that you can also play with this. So I think I have time to talk about the third example, and I wanted to show to you. It will be sort of similar to the second example, but I wanted to highlight here another feature of the technique that is worth seeing at some point. So here we will talk about a problem called QK cut, or it's sometimes called a nice cut or something like that. And the question is, we are given an undirected graph now, so this is a graph G, and we are given 2 numbers, Q and K. And the question is whether I can find a set X. This is my cut, yes, in my graph, of size at most K, yeah, such that when I remove it from the graph is being partitioned in sort of a balanced way. In a sense that after removal of X, certainly the graph can be shattered into several connected components, but I do not want to have all the components apart from one very small. I would like to have at least 2 components of size at least Q. Yeah. So after removal of X, I would like to see 2 large connected components. Good. So we will now make an algorithm with running time 2 power order of Q plus K times a polynomial, again an FPT algorithm. And by biasing the coin, you can also change the also make the error probability a bit different if Q and K are not really of comparable magnitude. Good. So this is our goal. So we will do a similar trick. We will color the vertices with two colors. So suppose I've got some solution X. Yeah, so this is my set X in my graph, such that I've got 2 large components. Yes, C1 and C2, and possibly several small ones around here. Maybe different color. Yeah, but I would like to have two of them. So the natural way, trying to mimic the strategy that we used so far, would be to say, okay, let's color it with 2 colors, and the good event would be that X becomes red. Yes, and the C's become blue. But now there is a problem with this idea, because the C's can be very, very large. I cannot hope, if I draw a random coloring, I cannot hope for the event that the whole C1 becomes blue, right? However, the only thing that I care about when thinking about C1 is that C1 has at least Q vertices, and C2 has at least Q vertices. So I do not really need to make everybody in C1 blue. In my random good event, yes, let C1 have some subset Z1 that is connected of size Q, and C2 also has some subset that is connected of size Q. So this is Z2. Yeah, so let me distinguish any connected subset of C1 of size Q and any connected subset of C2 of size Q. Yeah, and I will hope that only those subsets are all colored blue. Yeah. So again, my experiment is that I draw a coloring into 2 colors, red and blue, at random of the graph. And a good event is when the separator, the set X, becomes red, while both Z1 and Z2 become blue. Yeah. So in some sense, I do not require that the whole. Yeah.
There's a question for you. Is there any reason why we make them connected, like the Z1 and Z2?
This will become apparent in a moment. Yes, there is a reason why we're doing that. It will become clear when we will be looking for looking for a solution assuming the good event happens. Yes, so we are distinguishing some Z1 and Z2, and we care only about making them blue, right? Yeah, so in some sense, the Z1 and Z2, you should think of them as small witnesses that C1 and C2 have the required properties. Yeah, because if C1 and C2 indeed have Z1 and Z2, they are automatically of size at least Q. Right? So the good event is that the separator itself becomes red, while the witnesses, Z1 and Z2, they become blue. Right? So there are here 2 Q vertices in Z1 and Z2. There are at most K vertices in X that should become red. So again, by the same reasoning, the probability that the good event happens is 1 over 2 power K plus 2Q. Yeah, because this comes from this condition and this comes from this condition. Right? Okay, so now by repeating that many times, 2 power K plus 2Q, we can assume, and allowing for false negatives, we can assume that the good event happens. And now we are left with trying to find a solution, assuming the good event happens. Right, so again, because in a good event, the solution X, the separator X, should be disjoint with the blue vertices. Yes, because X should be entirely colored red. This means that if I look at my graph after the coloring and I look at the blue components, yes, they are entirely not cut by the separator X. So each of those blue components, they will stay connected after the removal of my separator X. Yeah. And observe that if Z1 and Z2, these are 2 guys, Q, of size Q, that should in the good event become blue. Then there are 2 components, blue, one entirely containing Z1 and second entirely containing Z2. Yeah, these 2 components should be different. Blue components should be different because Z1 and Z2 should be separated by the solution X, which should be entirely red. Yes, and these blue components are of size at least Q because both Z1 and Z2 are of size Q. So Z1 and Z2 alone already certified that those blue components are of size at least Q, right? And here is the answer to your question: why we required Z1 and Z2 to be connected. Well, I wanted Z1 and Z2 to be entirely contained in one of those blue connected components, and this is why I wanted it to be connected. So now it comes the algorithm. I look through all possible pairs of blue components, say D1 and D2. So, and D2, D1 and D2. So in a sense, by trying all possibilities, I guess the 2 blue components that should contain Z1 and Z2. And if I identify this D1 and D2 by trying all possibilities, I just compute a minimum cut between D1 and D2, a minimum vertex cut between D1 and D2. Yeah, so I find some minimum separator in the graph that separates D1 from D2. And this I can do using MaxFlow min cut algorithm in polynomial time. Yeah. So now observe what happens. Certainly, if we found such a cut of size at most K, then we found a solution, right? Because after removal of this cut of size at most K, yeah, I have 2 connected components, one containing Z1 and second containing Z2, and both of them are of size at least Q. On the other hand, if I had the good event and I guessed D1 and D2 correctly, then I will find such a cut because my solution X is such a cut that separates Z1 from Z2 or D1 from the D2. Yeah. So if in the case of a good event, I will be able to find some proper some feasible solution to the problem. Yeah. Yeah, so all in all, getting back to the repetition, we are repeating the algorithm 2 to the k plus 2q times, each time solving the trying to find a solution in p time. And if we find a solution, then great. If no, we answer no, and we err with probability at most 1/2. Good. Are there any questions to this algorithm? Or otherwise, put a +1 on the chat so that we are happy. Okay, I feel that many of you got this algorithm. So during the last 10 minutes, I would like to spend on just stating basic facts about the randomization of color coding. And the important thing to remember is that essentially all, unless you're doing something really off, essentially all algorithms using color coding can be randomized. And there are standard pseudo-random objects known that allow for the randomization of color coding. So for the K-path algorithm, where we were looking for like colorful K-path, we will be using something called splitters. So what is an NAB splitter, where these are parameters? All of them are natural numbers. Yes. So imagine you've got some universe n, yeah, so numbers from 1 up to n, and you would like to hash it into a smaller universe. So in other words, color it. So you have here B colors, yes, and each of the elements of your large universe needs to be mapped to some color from the smaller universe B. Yeah, so this is just a coloring, an idea of a coloring function. So a splitter is a family of coloring functions, yeah, with the following property. Whenever I pick here a subset of size, say A of size at most A, yes, there is some element of the splitter, there is some function of the splitter that's actually injective on this set A. So that maybe I can draw it anew. If here are my vertices of A, yeah, in the function in my splitter, they should be mapped to pairwise different elements in my smaller universe B. Yeah. So for every small subset of the universe n, there is some function in the splitter that makes this subset colorful. And observe that this is exactly what we wanted when doing color coding for K-path. We wanted the property that for every K-path, so more generally for every subset of K vertices, there exists some coloring. We would like to find the coloring such that this K-path is colorful under this coloring. Yeah. So obviously, if I took all possible functions from n to b, there are n to b of them, then I would find a good splitter, but this would be too costly. And the theorem from the theory of pseudo-random objects is that you can actually find an nkk splitter that is small, that is of size e power k times some quasi-polynomial factor k power order log k times logarithm in n. So this is almost this is very close to this probability error when we were choosing a function randomly. Yeah, recall that when we were choosing a function randomly, a k-path became colorful with probability e power minus k. And now this is reflected by the size of the splitter, which has this main term e power k, but there are also some additional terms k power log k and a log n term that correspond to actually working with a pseudo-random object. And this splitter can be constructed in good running time. Yeah, essentially in time that is its size times additional n. Yeah, it's essentially an algebraic or number theoretical construction that you just need to execute. Yeah. So now, how do you do the randomized color coding? So in the randomized way, when we were discussing it before, we were going through random colorings. We were sampling random colorings of the vertex set of the graph, and we were going through e power k of them, right? So now instead of doing this, we construct a splitter of this size, yes, and we are going through all possible functions in the splitter. And now the property of the splitter tells us that if there is a k-path in one of the elements of the splitter, it will be colored properly. It will be colored. Right. So for the randomization of the color coding, when you use two colors, we use some other pseudo-random objects. I think they're called universal sets. I did not find this particular definition directly in the literature, but I think that this definition can be somehow inferred from what is in the literature. So an NAB universal set is the following family of coloring functions. Yeah. Again, we have a universe of size n. Yeah, so say numbers from 1 up to n. And now we would like to color it with just two colors. So there are two colors in my image, 1 and 2. Yeah, so each vertex here is mapped either to 1 or to 2. Yeah, and I would like to have the following property that exactly corresponds to what we wanted in the in color coding. We wanted to have that if here is my universe n, and I find some subset A, maybe some subset B of size B, and some disjoint subset A of size A, yeah, then there is a coloring in my universal set, some coloring F in my universal set, such that, say, coloring like that, such that A is exactly on one side of the coloring and B is on the other side of the coloring. So this coloring distinguishes A and B, so such that A is on one side entirely and B is on the other side entirely, right? And again, there are NAB universal sets whose sizes almost correspond to the probability of error when doing color coding. So for the random flips, you've got a size 2 power A plus B times some additional factors, and there are also NAB universal sets for those biased coins. They're of size roughly this. And again, when you want to the randomized color codings using NAB universal sets, when you are drawing a random coloring into two colors, instead of drawing a random coloring, you just go through all the elements of an NAB universal set, and this does the job deterministically. Good. I think that this is all that I wanted to say about color coding. Are there any quick questions at the end? Thanks a lot for the attention, by the way. Hello, is anybody there?
Hi.
Yeah.
All of us are here.
Yes.
Yes.
Yeah. Any reason why they are called splitters and universal sets? Please ask this question to Noga alone or anybody else working in pseudo-random objects. I think that they are much more competent to answer this. All of this comes from hashing families. So splitters are also, I think, called universal hashing families. So these are objects that are studied most in the hashing literature, and this is the terminology that is somehow brought from there. But I'm definitely not an expert here, so maybe I'm using actually wrong.
Yes, now what you call a splitter, they just call a hash family. So for a splitter, they say that equal partition thing. That is why they call it a splitter.
Ah, really?
Yes. So if you look at this, the book paper of this guy, Nauer and all this, from where we got this term, he actually calls splitter something else.
Oh, so we were wrong the whole life.
Yes.
Oh, that is a bit embarrassing. Okay, good to know. Good, so universal hashing families. Yeah. But it's important to actually know what the object does and that it exists. Good, any more questions? So if not, then thanks a lot. I will join PC 301 later on after Christmas for another more advanced lecture, but I wish you Merry Christmas and enjoy the rest of the school.
Thank you.
Thanks, Michał.
Okay,
Thanks.
thank you so much. Thank you for the talk. And we wrap this session here.